Okay, so 4.1 part 4, we're going to talk about non-homogeneous linear differential equations. Here's our general form. Has coefficients in terms of x, g of x on the right. For non-homogeneous, where the g of x cannot equal to 0 by definition. So I'd like to define a particular solution, and we call that yp for particular. It's a solution to the dE, the non-homogeneous solution to this. It's a particular solution to it. No arbitrary constants. The complementary solution, yc, is the general solution to the homogeneous. So we've been already seeing that we can take the fundamental basis and write as a linear combination that for the homogeneous. So that's what that is. Think of C there as, it's for complementary, but think of it as having the constants in there. Okay, here's a big theorem, actually. Okay, so this theorem says, this is a theorem for the general solution of a non-homogeneous solution. So yp is any particular solution of the nth order homogeneous differential equation. So yp is a particular solution to the non-homogeneous, okay? And let y1 to yn be the fundamental set of solutions. Remember, if you take the fundamental set and you put arbitrary constants in front of them, it's the solution to the homogeneous. So this is what we have. The general solution to the non-homogeneous is y equals, this is yc, c1 to cn for each yn, plus yp. So basically, just in general, it's yc plus yp, where yc is the general solution to the homogeneous dE. I do want to prove this, but it's, again, a simple proof using the linear operator. So let's just write it out really quick. We need to show y equals is a solution to the nth order non-homogeneous, we'll just write it out, a(n)y n plus a1y prime plus a0 y equals g of x. Okay? But again, I want to call this Ly equals g of x. It makes it so much easier. So we want to basically show L, if you plug in this, that it's a solution to that equation, to this equation. So we can distribute, because that's what linear operators can do. So this also gives you an idea, exactly. So this yc is a solution to the homogeneous, so this is 0. This yp is a particular solution to the homogeneous. So that means it's equal to g of x. You plug it in, you get g of x equals g of x. And it looks like we showed it. There's actually a second part of the proof, and it's to show uniqueness. It's the only solution. So my favorite proof, if you're going to show that it's unique, well, we're going to assume there's a second one. So proof by contradiction. So assume U equals another solution to the non-homogeneous system. That's what we're trying to say, that that's unique. So using operators, that means you plug it in and you get the function g of x because it's a solution. Well, our second solution is our particular solution. That's what a particular solution, you plug it in to true statement. So now that there's two, we're going to actually subtract the left side and the right side. If I subtract g of x minus g of x, it's 0. Over here, it's just LU minus LYP. We're going backwards with the linear operator. So this is saying, looks like this is a solution to the homogeneous, because it's 0, right? D. So if it is, then minus YP would have to equal to YC, and U equals YC plus YP, and that's the same solution, which means contradiction. Okay, so we want to verify that this is the general solution to this DE. Now, what I want us to be able to do, I think this is a good problem because it helps us see these C's, the arbitrary constants. This is my YC, and this is a particular solution. We call that YP. So we can't just take this and take the first derivative and the second derivative and plug it in and show that it's a solution, because that doesn't prove that it's a general solution. So in order to be a general solution, we have to have YC plus YP. And then to show YC, we need to be able to show that it has solutions Y1 and Y2 right there, and that they are independent. So it forms the fundamental set. So let's write that out. To show general, we need, again, so our two solutions are x to the minus 1/2, x to the minus 1 is a fundamental set. We need to show these are a fundamental set for the corresponding homogeneous, which would be this equaling to 0. Okay. And then part B, we need to show YP is a particular solution. This YP that we did, YP, let's just write it out. For the non-homogeneous DE, basically this one. Okay, let's do it. So show the fundamental set, part A. We need to show y equals x to the 1/2 as a solution. So we need to plug in first derivative and second derivative. So let's plug it in. We only need to plug it into this one, the homogeneous. And then, so that's y prime, and then plus y. Okay, let's just do the math. This is 6. Two minus 5/2. One minus 3/2. And then find a common denominator, 2/2. Oh yeah, 0 equals 0. Solution. Do the same thing for the second set. -1, maybe a little easier. So plug that into here again. Show it's a solution. Double prime. And then last but not least, independent. Remember how to do that. We have to use the Wronskian. Take the derivative of the second line, find the determinant. It's got to be non-zero. Add the exponents. So -1/2 in the front. It's going to change things. So it's +1/2. So that's never going to equal to 0. It's got 1 on the top. So yes. Basically, it's a basis. Then part B, show that is a particular solution. So of the whole homogeneous, so we do just plug that in. So let's do it. Plug it in. And we've got to show it's a particular solution. That's what we're being asked. So we're just looking for a true statement. Combine those. I think you get 1. Combine. -6/6 is -x. So true. So by theorem. So that's our general solution of the homogeneous. That's it for today.